Hello, I am Agne, and I am a PhD student in Max Planck Institute for Extraterrestrial Physics. And today I'm very excited to share the work that I've done with my supervisor, Ariel Sanchez, Andrea Pezzotta, and eBOSS collaboration. And most of the things that I'm going to talk about today, you can find under this archive ID. So without any further ado, I'd like to start almost from the very beginning. I'd like to start from Planck, whose cosmic microwave background measurements all the way back at redshift of recombination allowed us to obtain the most precise measurements of cosmological parameters to date and confirm ΛCDM as our standard model. However, of course, Planck is only able to provide predictions rather than measurements of the values of these cosmological parameters to date. Luckily, we have a number of excellent low redshift probes that allow us to perform actual observations and measure the values of these parameters at low redshifts, which we can then compare with Planck's predictions, and in this way further test our model. And as you will have heard, the results of these comparisons are quite controversial. So first of all, there is the famous Hubble tension, which, to describe it in a very simplified way, simply refers to the fact that the rate of the expansion of the universe today, as predicted by Planck, is lower than what is measured by a number of direct probes. Most significantly, the measurement that is coming from supernova 1A is already today at 5 sigma above Planck's prediction. In addition to this, less significantly, and therefore perhaps even more controversially, Planck seems to predict a higher lensing amplitude than what is measured by weak lensing surveys. So here I've taken this plot from the kilodegree survey, recent cosmological analysis, and it shows different measurements of S8 cosmological parameter describing the weak lensing signal amplitude. Planck's prediction of this parameter is 3 sigma above what kids measured. In particular, the 3 times 2 point constraint is 3 sigma below Planck's prediction. A number of different weak lensing surveys, such as the YES or HSC, do measure a value that is closer to Planck. However, it is interesting to note that all of these different data points are below Planck's value. And most significantly, we see this data point coming from a combination of weak lensing and galaxy clustering full shape analysis from eBOSS galaxies. And this shows how these two probes are highly complementary to each other and can be used to further test our model. So inspired by this work, we want to build even further. And in this work, we present, first of all, a full shape of eBOSS quasar clustering analysis, which allows us to expand the redshift range covered by our clustering probes. We also reanalyze eBOSS galaxy clustering wedges with an updated model for power spectrum and bias modeling, which means that we are able to obtain tighter constraints. And finally, we combine our large-scale structure constraints with those coming from 3 times 2 point measurements from dark energy survey year 1 data release. So we want to see whether our low redshift probes constraints are consistent with each other and also consistent with Planck's CMB predictions. But before we go to all that, I'd like to say a couple of words on our measurements. So our clustering measurements for eBOSS are coming from Sanchez et al. And these are the clustering wedges that cover 2 redshift bins, covering a redshift range of 0.2 to 0.75. So we're not using this middle bin to avoid overlapping. And clustering wedges is just a 2-point correlation function that is measured in different angular bins mu, or angular ranges. So this orange wedge is measured perpendicularly to the line of sight, the blue one is measured parallelly, and the green one is measured in the angular range in between. And you can see how this amplitude change that is induced by the redshift space distortions is seen in these wedges. So it's just a way to express the anisotropic information of 2-point correlation function. For eBOSS, we are using quasar clustering multiples by Hu et al. It's just 1 redshift bin covering redshift range of 0.8 to 2.2. And clustering multiples is just a 2-point correlation function that is expressed in Legendre multiple basis. So here we see monopole, quadrupole, and hexadecapole. And yet again, it's just a different way to express the anisotropic information of 2-point correlation function. So I said that we are performing a full shape analysis, and therefore we need to model the power spectrum, the Fourier space equivalent of 2-point correlation function. And in order to do that, we need to model a number of important effects. So first of all, we need to model the redshift space distortions. For that, we're using the TNS model, and we also need some prescription for the small scale virial contributions. And for that, we're using this Cosmaro prescription for the finger of God effect. We also need to model nonlinear clustering. And for that, we're using Respresso, which is based on response function approach, and it's a mixture between simulated and perturbative approaches. This is the same recipe that was used for eBOSS analysis, but this is new for BOSS. For galaxy bias, we're using one loop bias and coevolution relations. The coevolution relations allow us to relate the tidal bias parameters gamma2 and gamma21 to linear bias B1, and in that way obtain tighter constraints by simply reducing the number of free parameters that we have in our model. And this bias model is also an update for our clustering analysis. And we have our model, we have our data. I'd like to say a couple of words on the parameter space. So the parameters that we're interested in here are motivated by this work of Sanchez 2020, who pointed out that as different probes recover different posteriors for Hubble parameter h, that means that any parameter that is defined through h will also depend on the particular posterior of h recovered by that probe. And this can be illustrated very clearly for the parameter sigma 8, which is just the density field variance as measured on a scale of 8 megaparsecs over h. And I'm illustrating this here in this panel above. I'm showing the posteriors for Hubble parameter for our different probes used in this analysis. So at the two kind of ends here of extremities, we see Planck that measures h extremely well, and DES that, being a weak lensing probe, does not measure h well at all. It has a rather wide posterior. And if we take a look at what physical scales 8 megaparsec over h correspond to for these different probes, we will note that for Planck, 8 megaparsecs over h is clearly just 12 megaparsecs. Nevertheless, for DES, the story is a little bit more complicated as it has wide posterior of h. 8 megaparsecs over h also correspond to a wide range of physical scales. We can also take a look at how that transfers to how that translates to the density field variance measured. Here on the y-axis, I am showing the density field variance as measured at different physical scales R, and I'm showing the ΛCDM Planck prediction here in dark blue, and the different posteriors recovered by different probes here in different shades. So you will see that for Planck, as it constrains h well, it corresponds to 12 megaparsecs. And we're actually, by measuring sigma 8, we're actually measuring the density field variance at a set scale. However, for DES, as its 8 megaparsecs over h correspond to a wide range of physical scales, what we are actually measuring when we're measuring sigma 8 is a weighted average of this quantity. And therefore, the two parameters kind of have different physical meanings for these two probes. And here I illustrated this for sigma 8, but the same is true for any parameter that is defined through h, so also for relative matter and dark energy densities. And in order to avoid that, in this work, we focus on physical parameter space. So first of all, we focus on sigma 12, which is just the density field variance defined on a physical scale of 12 megaparsecs. And we also focus on physical densities, physical matter and physical dark energy density. Right, so finally, it's time for the results. Let's take a look at BOSS and eBOSS first. So here I'm showing BOSS in blue, eBOSS in brown, the combination of the two in green, and Planck in dark blue. And you will see that all of these probes seem to be very consistent with each other. And indeed, if we take a look at the evidence-based tension metric that we use to quantify our agreement, we will see that BOSS and eBOSS agree with Planck within 0.6 sigma as measured by suspiciousness. We can also see that the value of sigma 12 that is recovered by our joint clustering probes is also in a perfect agreement with Planck, and that's actually also true for sigma 8 as well. However, we want to perform an even further consistency test, which is inspired by work of Sanchez et al. 2021 that classified cosmological parameters into shape and evolution parameters based on their effect on the power spectrum. So shape parameters are those parameters that describe the shape of the power spectrum, and for fixed shape parameters, evolution parameters only vary the amplitude of the power spectrum. So what we want to do here is we want to impose informative Planck priors on the shape parameters, physical baryon density, cold dark matter density, and the spectral index, and see whether recovered constraints on the evolution parameters, sigma 12, AS, and dark energy density are also consistent with Planck's prediction. So we're forcing our clustering constraints to select such cosmologies whose power spectrum shape matches that preferred by Planck's cosmology, Planck specific cosmology, and we want to see whether the amplitude will match as well. And here are the results of that. So in gray, I'm just showing the same constraints you saw in a previous slide, white prior analysis, just what you saw before. And in green, I'm showing what happens once we impose this informative prior. So now NS and the matter density match Planck's posterior exactly by design. And the constraints on the evolution parameters actually seem to be very consistent too. So perhaps AS is slightly lower and sigma 12 is slightly lower than Planck, dark energy density is slightly higher, but overall, everything is very consistent. So everything's great, we can move on. Now let's look at what happens once we add DES. Adding DES does degrade the agreement with Planck slightly. So the combination of BOSS, eBOSS, and DES agree with Planck within 1.5 sigma based on suspiciousness. So slightly less good than BOSS and eBOSS, but still very consistent. However, I would like to point out a couple of particular parameter combinations. So first, let's take a look at matter density and sigma 12. DES is shown in light blue, and it is in a perfect agreement with the Planck constraint in dark blue. And this is, if you remember correctly, this is not what you saw in the traditional parameter space. So here I'm just showing that again. So normally, if you look at the combination of the matter density and sigma 8, there is this DES banana, which is roughly 2 sigma below Planck's prediction. And we compare the two, we can see that this discrepancy in omega matter sigma 8 space only appears when these megaparsec over H units are used, at least for these data sets. That is important to note that the combination of BOSS, eBOSS, and DES together in orange is still below Planck. However, that only happens when the three probes are combined. However, that doesn't mean that all is well and great in our physical parameter space. And now I would like to draw your attention to AS and sigma 12. And here, both DES on its own and its combination with BOSS and eBOSS here in orange are roughly just over 2 sigma in tension or in some discrepancy with Planck's preferred values. And this has a very clear physical interpretation. So for a selected value of sigma 12, Planck prefers a lower value of AS. So it means Planck prefers slightly more total structure growth than the large scale structure probes. And if we compare this result with what we saw in the traditional parameter space, you will see that as traditional parameter space is not able to recover this tight degeneracy that we see in physical parameter space, we also don't see this discrepancy. So in this particular case, the physical parameter space allows us to, first of all, recover this physical connection between the two parameters, but also have a clear interpretation on what discrepancy we see and what it actually means. Now, if we perform the same consistency test by imposing Planck-like priors on shape parameters again, we will note that this time the shifts we see in evolution parameters are somewhat larger than what we saw for clustering alone. So sigma 12 and AS are recovered 1.9 and 1.2 sigma below Planck values, and the dark energy density is recovered to be 1.7 sigma higher than what Planck prefers. And this again is very consistent with what we just saw before. So of course, in a universe with slightly more dark energy density, we do expect to see less structure growth. And this is not something that we can normally see in our analysis because BOSS, eBOSS, and DES do not constrain the dark energy density well. Right, so hopefully I piqued your interest in dark energy now. And the next step that we did is we try to analyze alternative dark energy models. So now we allow the dark energy equation of state parameter W to vary freely. We perform the same analysis within wCDM model. And here you see the results in traditional parameter space, BOSS and eBOSS in light blue, Planck in dark blue, the combination in red. And you see that now we have these really large degeneracies because Planck does not constrain H0 anymore. We can see clearly why that happens if we look at the physical parameter space on the left-hand side. So the value of H0 today is, of course, just the sum of the physical matter and dark energy densities. The physical matter density is still constrained well. However, that's not true anymore for the dark energy density because the evolution of dark energy is not fixed anymore, and Planck does not have any low redshift information. We're not using any CMB lensing here. And as a result, any parameter that is defined through H, such as omega matter or sigma 8, are also not constrained anymore because they're averaged over this wide posterior. However, as only certain values of W and dark energy density are allowed for Planck, the clustering amplitude is actually still constrained even in wCDM scenario. And you see that when we look at the physical parameter space and at sigma 12. So actually, let's take an even closer look to that. So here in the top panel, I'm showing the constraint for sigma 8 for lambda CDM and for wCDM. And in the bottom panel, I'm showing the same thing, but for sigma 12, in both cases for Planck. And you'll see that actually Planck constrains sigma 12 just as well when W is allowed to vary as it does when W is fixed to -1. And all of this lack of constraining power on sigma 8 is simply because of this averaging over the posterior of H, which is no longer constrained by Planck in these cosmologies. And therefore, this work will be the first one to present a constraint on the power spectrum amplitude today in wCDM cosmology from Planck. So I'm super happy to be showing you this and to be showing you that this probe that we know so well is actually even more powerful than we thought. However, perhaps less encouraging news are that the value of sigma 12 that we do recover for Planck is actually higher than what we had in lambda CDM. So it doesn't really help us to reconcile it with the large-scale structure probes at all. But yeah, this is my time. I will leave you with my summary of this talk here. Thank you very much for listening, and I will be very happy to answer any questions that you might have. Thank you very much.